the 21 centimeter power spectrum from the cosmic dawn and epoch of reionization. So let me start by first going through what these epochs are in the timeline of the universe and what do they tell us and how we can probe these eras in the universe's history, right? So at a very high redshift, starting from an initial hot and dense state where the matter was coupled to the plasma, the universe was expanding adiabatically and the temperature was falling down. And at a redshift of around 1100, the temperature was cool enough for the electron and protons to combine with each other to form the neutral hydrogen in the medium. So this is an epoch that is known as the epoch of recombination. Now, due to the sudden decrease of the electrons in the intergalactic medium, the matter and the photons decoupled with each other, creating this CMBR that we observe today. And the tiny matter density fluctuations that were coupled to the brightness temperature distribution of the CMBR, because the matter was coupled to the photons prior to the recombination. So these tiny matter density fluctuations start growing by the means of gravitational instability during the dark ages, up to a redshift of 30, where the first luminous objects could be formed. Now here in this picture, this blue shows the neutral hydrogen part of the IgM, and the white portion shows the ionized part of the intergalactic medium. So at around redshift of 30, these first luminous sources are emitting X-rays and UV photons that are heating the region, intergalactic medium around them, and ionizing the neutral hydrogen in the intergalactic medium. So at the beginning, we see this small ionized region forming, which as reionization progresses, overlap with each other up to a redshift of 6, when the universe is almost completely ionized, and post this EOR, epoch of reionization, hydrogen only resides in this discrete high density H1 columns, which has column densities of around 10 to the power 20 atoms per centimeter square. Right. Now, this cosmic dawn and epoch of reionization are related to some of the most fundamental questions in astrophysics and cosmology, such as the formation of the first galaxies, properties of perimeter poor stars. Then the large-scale structure distribution in itself is a very powerful probe of the expansion history of the universe, and it can also constrain various cosmological model parameters and models.
There is a question,
which is why it becomes clear that we can learn a lot about our universe by looking into these looking into this time frame of our universe. Right?
Srijita, can you
How
hear
do we probe this cosmic dawn and epoch of reionization? So the
Srijita, hello, can you?
Is the 21 centimeter signal,
Srijita, can you hear
which
me?
is emitted, which is a line that is emitted due to the hyperfine transition of the H1 atom. The spin parallel state is known as the triplet state, and when the spin becomes anti-parallel, it goes to the singlet state, and this transition emits a photon. Hello? Is it turning now? This is at full screen actually. But it's changing now, right? The slides are changing. Which slide is it showing? Yeah, it is at slide. Now, is it changing? Okay, so let me stop share for once. Yeah. Is it working now? Is it full screen now? Is it full screen now? But it's showing full screen for me.
I think if she is doing this full screen, then it is coming as a different pop-up, and she has only shared the PDF file. So better ask her not to do the full screen and only use the window which she shared, or share entire screen.
Sorry. Okay, let me see. But I am sharing my entire screen only. Can you see it now?
Yes, now it's clear.
Okay. Okay. So yeah, what we are trying to do is we are trying to look into the EOR and cosmic dawn using the hyperfine transition of the neutral hydrogen, which emits a radiation at 21 centimeter. Now, the probability of a spontaneous emission is actually, for this particular line, is actually very low. So the Einstein A coefficient is of the order of 10 to the power minus 15 second inverse. Which corresponds to a lifetime of around 10 to the power 7 years. However, the sheer abundance of the hydrogen atom, the neutral hydrogen atom that is present in the intergalactic medium, and the ability of the Lyman alpha coupling and the collisions to pump the electron from the singlet state to the triplet state allows for us to get a signal that can be detectable, right? So this low probability of spontaneous transition is easily overcome by these two factors. Another point to note here is that even though the signal is emitted at a frequency of 1420 megahertz, or corresponding to a wavelength of 21 centimeter, because of the expansion of the universe, this line redshifts, and we observe the line at a lower frequency, which depending on the redshift is given by this relation over here. So when we are measuring the signal at a low frequency, at a certain frequency, that means that the signal is coming from a particular redshift or a particular distance, and we are looking at a previous time of the universe, right? So here, basically the frequency corresponds to the line of sight distance information for us. So what we are trying to do is we are trying to do intensity mapping with the 21 centimeter signal, which is a complementary approach to the optical surveys, the spectroscopic and photometric surveys that are historically been used to basically observe the high redshift universe. However, note that the 21 centimeter signal may be the only way to probe the dark ages where there were no luminous objects. So what we try to do is, so the brightness temperature fluctuation of the 21 centimeter signal traces the conditions within the IGM through a suite of radiative and collisional processes. Thus, the spatial structure of the signal as a function of redshift traces the evolution of the first ionizing sources of radiation, right? And the detection of the absorption and or emission of the 21 centimeter signal can be used as a tracer of the underlying matter, or as an indirect proof of other properties of our universe, such as its ionizing state or temperature. So another factor here is that the 21 centimeter signal is optically thin, which basically means that when the signal is coming from a distance to the observer, the probability of the 21 centimeter photon getting absorbed or emitted in the intergalactic medium more than once is very low, right? So it allows for a 21 centimeter signal to traverse the IGM and reach to our telescope where it can be detected. And this allows us to make this 3D images of the 21 centimeter signal. So this is the technique that is known as the intensity mapping of the 21 centimeter signal. So what is the advantage of the intensity mapping? So the 21 centimeter signal that is coming from the high redshift universe is very weak in strength, especially compared to other sources in the sky. However, fortunately, to study the large scale structure, we do not need to detect the galaxies individually, and instead with intensity mapping, we can integrate the signal over these large volumes of observation, thereby increasing the strength of the 21 centimeter signal. So by statistical detection through power spectrum, we are basically integrating over these large volumes of observation, and we are increasing the strength of the signal so that it has a better probability of being detected. So the system that we are considering is, so here's the CMB background at a temperature T gamma, and the CMB photons are coming through the intergalactic medium where it is getting absorbed and emitted, and some brightness temperature is being recorded over here at the observer, right? Now this T gamma for the 21 centimeter signal interacts with this intergalactic medium through the spin temperature of the 21 centimeter signal, which is a quantity that basically quantifies the ratio of the neutral hydrogen in its triplet state to the ground state. So this ratio is equal to G1 by G0, where these are the degeneracies of the triplet state and the singlet state. So G1 is equal to 3 and G0 is equal to 1. T star is a constant, which is basically is equal to energy of the 21 centimeter photon divided by the Boltzmann constant. So it has a value of around 0.068 Kelvin, and Ts in the spin temperature. So we can see that spin temperature basically quantifies the ratio of the population of the neutral hydrogen in its triplet state to its singlet state. So this T gamma that is coming through the IgM is getting absorbed by this e to the power minus tau factor. And because of the spin temperature or population of the 21 centimeter signal, some emission is also observed, which is given by this term over here. Now here, this tau is the optical depth, which are basically related to some of the cosmological parameter and also to the peculiar velocity of the photons in the intergalactic medium. So the net signal, that the net brightness temperature fluctuation that will reach us is given by this expression. However, what we are interested in is the excess brightness temperature over the CMB that we are observing. So T gamma minus T tau minus T gamma, and this gives the expansion of the universe. And we can expand this e to the power minus tau, and tau is much less than 1 for the 21 centimeter signal. So this T tau can be approximated so that this term can be written as this over here, and we can substitute the value of tau from over here so that the excess brightness temperature fluctuations against the CMB can be written as a function of two terms, multiplication of two terms. One is this T bar, which basically contains these cosmological parameters and is a function of redshift or line of sight distance only. And there is another function, this eta h1, which is known as the 21 centimeter radiation efficiency. So this eta factor evolves not only as a function of the redshift or the line of sight distance, it also captures the spatial fluctuations of the 21 centimeter signal, right? And this is the system that we are considering. So here is an observer who is observing an observation volume in the sky where this frequency substituting for the line of sight distance information, and this theta is the two-dimensional vector in the plane of the sky that we are considering, and this box is at a distance r or r nu at a distance r nu from us. Now this factor T gamma by Ts is what determines whether we will get the 21 centimeter signal in absorption or in emission. For example, during the cosmic dawn, the spin temperature is coupled to the gas temperature, which is lower than the CMB temperature. So Ts is greater than T gamma, which makes this quantity negative, which means that during the cosmic dawn, we expect the 21 centimeter signal to observe in absorption. However, during the EOR, so the spin temperature is still coupled to the gas temperature. However, due to the X-ray heating of the intergalactic medium, the gas temperature easily overshoots the T gamma. So for EOR, T gamma is less than the spin temperature, which makes this term positive, and we are expected to see the 21 centimeter signal in the emission. So this shows the absorption during the cosmic dawn, and here we see that we are expected to, in EOR we are expected to see the signal in emission, right? Now this eta factor here it is written as a function of the spatial coordinates and the redshift. This can be decomposed into its Fourier components like this, where eta tilde is the Fourier coefficient of the Fourier series, and this eta tilde can be correlated at different k modes, which gives us the power spectrum. So the correlation between the eta tilde between two k modes, k and k prime, it gives us the power spectrum, where we see this delta function denotes that the power in the two k modes are uncorrelated. So only for k is equal to k prime, we get the power spectrum, otherwise the power is uncorrelated. So this comes from the assumption that our 21 centimeter signal is statistically homogeneous and isotropic, which gives us this delta function, and which shows us that the power is uncorrelated. So the power spectrum for the brightness temperature fluctuations will then given by this T bar square into this factor. So by measuring this, we can relate this to this PH1KZ, which is something that we can predict from our models of reionization or cosmic dawn. And so by measuring this, we measured this quantity, and we can then infer about various cosmological models and model parameters using the 21 centimeter line. So the question becomes that then how do we determine this brightness temperature fluctuation correlation using some radio interferometric observation? So for this, let me first start with the quantity called visibility, which is the basic quantity that is measured in any radio interferometric observation. So the idea here is that here is an electric field in the sky that is causing some electromagnetic, that is generating some electromagnetic wave that is propagating through this intergalactic medium and reaching us at this small r vector on Earth, right? Now so the entire field in the sky will give us some resultant field in the Earth over here, and the correlation between this field observed on Earth between two different places, R1 and R2, is known as the visibility. Okay, so the correlation of the resultant electric field at two different locations gives us the visibility. Now, given some assumptions, we can show that this visibility is basically this electric field on the sky at different locations, and this is the propagator propagator, which denotes how the wave will propagate to us through the intergalactic medium, and this integral is over the entire field of view of observation, right? Now we can so now there is another assumption that this fields at two different locations. So we are assuming that the electric field that we are observing are spatially incoherent. So again, this is correlated only if R1 is equal to R2. So we can use a delta function over here and do one integral to show the visibility is given by this equation. And here, this term is basically what is known as the specific intensity. So this is basically the energy that we observe per unit area, per unit time, for per unit frequency separation, and coming from a unit solid angle. So this energy is known as the specific intensity. And again, using the Fraunhofer diffraction limit, we can show that this is equal to d omega. This term goes to d omega, and this e to the power term can be written as a function of the difference between two R1 and R2 on the Earth. So if we have two telescopes over here, then we are correlating the electric field over here. We see that the visibility depends only on the difference between the locations of the telescopes on Earth, and this dot s cap means that the component of this antenna separation towards the sky as observed from the point source is what is known as the baseline. So we are measuring the visibilities at a baseline, which is basically given by this R1 minus R2 in dot s cap by C into nu by C. And using small sky approximation, we can write in terms of this two-dimensional vector theta on the sky over here, where I theta nu is the specific intensity distribution, and here this A theta is the beam pattern. So because of the finite extent of each telescope antenna, it will have a directional dependence. So from some directions, it will receive more energy than other directions. So that intensity pattern is taken care using this primary beam pattern over here. So visibility is essentially the Fourier transform of the specific intensity multiplied by this primary beam pattern over here. Now this specific intensity we can decompose into two parts. One is I bar, the mean part, and a fluctuating part. So if we transfer this in this equation, then this I bar comes out and you are left with only the Fourier transform of this primary beam pattern, which is written here as the small a u nu, and there is another part which captures the fluctuating part of the specific intensity. Right. Now the field of view A theta, the primary beam pattern A theta, actually goes by lambda by the diameter of the telescope, which means that its Fourier transform small a u nu will have an extent of diameter by lambda. So beyond that diameter by lambda distance, it falls off to 0 or a very low value. And most baselines are larger than this diameter by lambda length, most baselines that we consider for our studies. So which means that for our studies, this factor becomes negligible, or we can ignore this term. And for us, the signal part of the visibility only picks up this fluctuation of the brightness, temperature, or specific intensity in the sky. Now, in the Rayleigh-Jeans limit, which is basically the low energy limit, we can write this specific intensity in terms of the brightness temperature fluctuations, where this 2 kb by lambda naught square. So this 1 plus z comes because of the expansion of the universe. This is a constant term, and it is related to specific. So the specific intensity is basically proportional to the brightness temperature fluctuations. And if you remember, this delta t is equal to some t bar into eta h1. So this factor into this factor can be written as I nu bar, which can be calculated and shown to be have a value like this, and this factor eta h1. Now this eta h1 correlation gives us the power spectrum. So, and this delta I is related to eta h1 using this relation, where we have written it in terms of k parallel and k perpendicular. So this theta, for this theta, the Fourier component is u vector, and for the spatial fluctuations in R space, we decompose in Fourier space, we decompose it in terms of k parallel along the line of sight distance, and another component k perpendicular, which is perpendicular to the line of sight distance. Right, so k vector is decomposed in these two parts. So k perpendicular becomes related to the baselines using this relation, and this Fourier transform of frequency, which is this tau or delay, is related to the k parallel vector using this relation, where this r nu prime is basically dr d nu. So using this, we can show that if we correlate the signal at two different baselines and at two different frequencies separated by a frequency separation delta nu, then that becomes proportional to this power spectrum that we want to calculate. So this is equal to some constant into this primary beam terms into this power spectrum. Now there are assumptions which we can use so there are assumptions, valid assumptions, where this term can be taken as a constant and it can be taken out of the integration. So then it becomes and then the integration is over this a and a star, which is easily calculable. You can easily calculate that term. So then this factor becomes proportional to what is known as the multi-frequency angular power spectrum, which is the Fourier transform of this pH1k along delta nu. So in this expression, we see that this u is in Fourier space and this nu is in real space. However, we want the three-dimensional power spectrum in the Fourier space. And we see from this relation, it is related to the three-dimensional Fourier power spectrum through a Fourier transform along delta nu. So we can measure this quantity and take a Fourier transform along the frequency axis along delta nu to get the three-dimensional power spectrum over here. Another way to do is, so we have u in Fourier space. So we first Fourier transform to go from nu to the tau space. right? And then correlate to get the power spectrum. So which is what is shown here. So we go to the u tau space by taking a Fourier transform along the frequency, and because of this delta function over here, so different at different tau modes the power is uncorrelated. So the signal correlation in the delay space will then become some constant factor into the power spectrum in the Fourier space, where this V naught is essentially this integration over this two primary beam patterns that we have shown, and it comes out to be a constant quantity for us. So if so this is how the three-dimensional power spectrum is related to the signal part of the visibility. However, the signal part is not the only contribution to the visibility that we have. So along with the signal, we will also have a system noise, which will be there as an additive term in each visibility along with the signal. However, we assume that this noise at different baselines and at different frequencies and at different times of observation are uncorrelated. So we assume this noise to be a Gaussian random variable with some mean 0 and with some value of sigma. So because of this assumption that is this Gaussian random variable, so we can show that this noise at different baselines, frequency and different time is uncorrelated. So to avoid this noise bias, all one have to do is have to correlate the visibilities at two different baselines that are slightly separated from each other, or correlate visibilities measured at different times, even for the same value of u. So till now, we were discussing only about the visibility-based estimation. There's also an image-based power spectrum estimator, which I included because the SKA data challenge will also provide us with this image data cube. So we have the visibilities in this plane, where this is the u vector plane, uv, and this is the frequency axis. Now, one way to do is to make a map and go to the image plane, where it is the theta vector in this plane and the frequency in this plane. Then we can make a three-dimensional Fourier transform to go to the uv and tau space. And after going to the uv and tau space, the power spectrum then becomes mod square of the delta t at each k values, properly normalized by the volume of the observation. However, propagating statistical errors in this process is somewhat tricky. However, this is the basic idea of how you can measure the power spectrum using image-based power spectrum estimators. So there are several radio telescopes that are being used to try to detect the 21 centimeter signal from the EOR and EOR specifically. So there's GMRT, LOFAR, MWA, HEDA, and also the future telescope SKA, which is expected to detect the 21 centimeter power spectrum with high precision. And as for the what is the progress of the 21 centimeter power spectrum observation, so the current limits are given by HEDA. So the most sensitive upper limits on the 21 centimeter UR power spectrum comes from 94 nights of observation using phase 1 of HEDA, where they have given the upper limits on the power spectrum at 2 redshifts, Z is equal to 9 and 10.4, where they have reported 2 sigma upper limits at these k values, 0.34 and 0.36 HMPC inverse. And from their results, we can see that they have reported that many of the observed points, many of the power spectrum are consistent with noise. And the limits that they have provided, so that provide updated constants of astrophysics of reionization and the cosmic dawn, where they have ruled out a number of cold reionization scenarios using their limits that they have obtained. So now, what are the challenges of the 21 centimeter observation? So 21 centimeter signal is not the only signal that we are observing at our low frequencies, right? So all the other astrophysical radiations other than the 21 centimeter signal constitute the foregrounds for the 21 centimeter signal. And this foregrounds include galactic diffuse galactic synchrotron emission from our own galaxy and other galaxies, free emission from our own galaxies, and other external galaxies, and also extragalactic point sources, out of which at UR frequency we see the DGAC is the most dominant component in the foregrounds, followed by the extragalactic emission at 27%. So the visibility now has the signal part, the noise part, and in addition to that, the foreground part, which is found to be 4 to 5 orders of magnitude larger than the 21 centimeter signal that we are trying to observe. So these foregrounds are so much higher in magnitude that even the weaker part of the foreground, such as the free emissions from our own galaxy and the external galaxies, even these weaker components completely dominate over the H1 signal that we are trying to detect. Which is why it becomes clear why it is important to analyze the statistics and characterize and deal with the foregrounds for the 21 centimeter studies, why it is essential and integral part of the of all the intensity mapping experiments. So let me start by talking about the extragalactic point source. So I'm going to talk about extragalactic point source and the diffuse galactic synchrotron emission, which are the two of the most dominant components in our 21 centimeter studies. And both of these are characterized through a quantity called the angular power spectrum, which is basically the visibility correlation at the same frequency nu. Right. And this point source is expected to have two contributions. One is the Poisson contribution due to the randomness of the point source distribution, and another is the clustering part. And the contributions can be calculated using these relations, where this del B del T is essentially that 2 kb by lambda square factor. Right, and this S is the flux of the source, and dn ds is the source count, number of source dn in the flux limit ds, which is proportional to the flux itself, and it can be shown and it is characterized by this power law s to the power minus epsilon, where this epsilon is also dependent on the flux limit. And the and you can see that the clustering part, we have this extra quantity WL. This WL basically quantifies the clustering. So it is the Legendre polynomial of the 2-point correlation in theta space. So if you have radio galaxies, you can calculate the 2-point correlation function corresponding to that W theta. And if you take the Legendre polynomial, so that will give you the WL part. So using this, you can quantify the clustering part and the point source contribution of the Poisson contribution of the point sources to the angular power spectrum. Then there's DGAC, which has been measured in a broad range of frequencies from 10 megahertz to 100 gigahertz actually. So this shows the DGAC, this shows the Haslam map at 408 megahertz frequency, and it is this angular power spectrum of the DGAC is characterized in terms of a power law, where this L is essentially 2 pi into the baseline U. And this gamma has been characterized using many observations at UR frequencies, which suggests that it has a value around 1.823. However, this value differs when the direction you are observing changes. So it is dependent on the direction that you are observing. Here we show the 3 contributions from the DGAC, which is supposed to go as around L to the power minus 2. So this is the clustering part of the point source, which is a bit so DGAC is a bit steeper than this, and the Poisson part of the point source contribution, which is independent of L, it is constant. Now you can see that these are in the hundreds of millikelvin square range, right? And another important factor to note is how the frequency decorrelation of the power spectrum of the foregrounds go, because this is what is used to separate the foregrounds from the 21 centimeter signal. So it is characterized through the multi-frequency power spectrum, which is the visibility correlations at 2 different frequencies. And these can be written as a power law like this. So for the angular power spectrum, where nu A is equal to nu B, it is proportional to CL into nu A to the power minus 2 alpha. And this alpha has been also characterized using many observations, which suggest that it has a value of around 2.8 to 3.2. right? So we see that the foregrounds are smooth in frequency. And even when we, so if we consider this nu b to be is equal to some nu a plus some frequency separation delta nu, and we expand it, then we get that the multi-frequency angular power spectrum as a function of delta nu is also a smooth function in frequency, right? So this shows the CL delta nu for the foregrounds uh, at a frequency of 153 megahertz, where at different L values, they have shown the measured CL delta nu, and we see that the foregrounds decorrelate over a frequency of more than 2 megahertz. Now this shows the same CL delta nu for reionization for the signal at 130 megahertz, right? So these are different values of u's. So one value of u is equal to, so this u will correspond to an L of this into 2 pi. So around 600, suppose. Okay. And here it is in Jansky square. However, it is here in millikelvin square. So the correspondence is about roughly of 10, a factor of 10. Okay. So we see that at various L values, the signal decorrelates within the 0.4 megahertz to 0.8 megahertz frequency separation, which is much smaller than the foregrounds that we are observing over here. And we can see the amplitude comparison also. So this is almost 1.4 into 10 to the power 4. And here it is around, in millikelvin square, it will be around 10 to the power minus 7. So there's a huge difference in amplitude. However, this decorrelation in frequency is what one plans to exploit to separate the signal from the foregrounds, because so this is the Fourier space in K perpendicular, K parallel space. So K perpendicular corresponds to a U value, and this K parallel is essentially the Fourier transform of the frequency, right? So because the foregrounds are smooth varying functions in frequency, which will mean when we take the Fourier transform and go to the K parallel space, it is expected to fall off faster as compared to the signal part, which, because it decorrelates faster in frequency in the delta nu space, which will mean that in K parallel space, it will decorrelate slower than the foregrounds in this K perpendicular, K parallel space, right? So which means that the foregrounds are expected to be confined within this region in the Fourier space, and there is this window which is essentially known as a 21 centimeter window, where one can hope to detect the 21 centimeter signal. However, it must be noted that there are various instrumental effects and other systematics which bakes this spectral smoothness and introduces these oscillations in this foreground multi-frequency angular power spectrum, because of which this, instead of being confined to this region only, the foregrounds also spill over to the 21 centimeter window that we are trying to observe. So which is what jeopardize, but this idea where this foreground is confined within this region and this window opening up to for 21 centimeter signal measurement is what is known as the foreground avoidance technique. However, in this technique, we lose out all the information that is here in this lower K region, which is where the signal is expected to be more stronger, right? And also by removing this foregrounds from here, we can also decrease the leakage that is there in the 21 centimeter window portion, right? So which is why people try to model the foregrounds and remove it from the data. So there are many techniques that are available in literature of how to remove the foregrounds from the data. However, most of them are at least use the same principle, that the frequency decorrelation of the foregrounds is slower than the signal. So okay. So there are techniques which try to take the image and take each pixel and try to fit a polynomial, suppose a smooth polynomial function through the spectra, and try to subtract that from the data. This can also be done in the UV plane, which is a section of the foreground fittings which are known as the parametrized bits. In non-parametric fits, there are no a priori functional forms to describe the foregrounds. Instead, they provide a quantitative criterion by which to judge the smoothness of the spectra, and then they allow the smooth portions of the data to be fit out. The Gaussian process regression is an example of the non-parametric fit, where they basically take the signal and foreground covariance and also the systematic parts, and they use the frequency covariance to model it using various kernels. And given those models of kernels, they then basically calculate the posterior of the new data given the actual data that we have. And then that new data which is expected to basically represent the foregrounds is then subtracted from the visibilities of the actual data. And the residual data in GPR is expected to only have the contribution from the noise and the signal, one hopes at least. Then there is another section of foreground removal process, which are known as the mode projection, where the idea is to express the data in some basis function, and to zero out the contribution from selected bases where the components are believed to be dominated by foregrounds. So one example of such technique is the principal component analysis, where they again take the frequency covariance matrix from the data, and they perform an eigenvalue decomposition to identify the strongest mode in frequency, which then are projected out, considering there are negligible signal in those modes. So this has the advantage that it does not assume any spectral smoothness of the data, and hence it can capture the instrumental effects also, which breaks the spectral smoothness for the foregrounds. However, because they don't use any model for the foregrounds, which means that this runs the risk of over subtracting the foregrounds from the data, and which means some of the signal part will also go out in this process. So there are many more techniques of foreground removal that are present in the literature, and one can look up. However, other than the foregrounds, there are other factors such as the instrumental systematics, polarization, leakage, mutual coupling, ionosphere, radio frequency interference, which is the interference that comes from the earth itself, and also how to quantify this after going through so much processes of analysis. How do we quantify how much signal that we are losing in our process? So these are some of the challenges that are there for the 21 centimeter power spectrum estimation. Which brings us to the SK data challenge, which I will stop here and ask Shomita to continue from this part.
Yeah, thank you, Srijita. So, okay, I will start that, but before that, people, if you have any questions, so you can ask Srijita now.
Hello.
Yeah, Srijita, you can you hear us? I think no. Let me call. Srijita, I think you can't hear us, but if you have been, so if there is any question, I'll just repeat to you. If you have any questions, please ask. I think. Okay, I think there are no questions. So thank you, Srijita, again. Let me start.
Hello.
Yeah, please. Yeah.
Hello. Yeah, I was just wondering if these slides video will be shared as well.
Yes, we will share all of these. Yeah.
Okay, and to read further about these, what will be good references?
References for this power spectrum of these things.
Yes.
Okay, we'll share that.
EOL physics and.
Okay,
yeah.
We'll share the references also. Yeah.
Thanks.
Okay. Okay, Srijita, thank you. There are no other questions. So let me start the data challenge then. Yeah. Thank you, Srijita. Yeah.
Okay.
Can you see my screen?
Yes, yes.
Okay, okay. So basically, this is not my slide. This is the slide from the SK observatory people. There, this is the slide I attended one of the talk by Anna Bolandi, and she is mainly organizing this data challenge 3. And I will just summarize what is this data challenge actually about and what the things we have to do. Okay, this is the slide. Okay, so the data, this is key. This data challenge 3 is divided into 2 parts. One is for the foreground subtraction, and another is the inference of the cosmological 21 centimeter parameters. And this is for the whole year 2023. The first 6 months will be for the foreground subtraction challenge that we have already applied for submitted the proposal, and the next challenge will start from I think it is July to December, but this is now only the foreground part is active. And the challenge will be the data is what Srijita said, that in the data there will be a simulated data for the SK, and there are a lot of corruption due to the point source, due to the foregrounds and different types of foreground. For example, the bright point sources, diffuse foreground from the data. And now we have to remove the challenges. We have to remove them using different techniques. What Srijita mentioned, the Gaussian process equation, non-parametric, all parametric, all PCR component analysis. There are different types of algorithm out there in the literature. We have to test which works better for the SK, but if people have any other ideas, that will be also useful for us. So challenge is somehow in some techniques, we have to remove the foreground. Now, from this foreground subtracted data, we have to extract the cylindrical power spectrum. So the cylindrical power spectrum is basically the power spectrum in a K perpendicular and K parallel space, or the K are the different Fourier modes. K parallel is the Fourier modes along the line of sight, and K perpendicular is the Fourier modes perpendicular to the line of sight. So in this cylindrical space, we have to estimate the power spectrum, and we have to compare with what the simulated data for the 21 centimeter only. So that is the data challenge, and verification of the result is compare this estimated power spectrum from the original input power spectrum. And so these are the person, Andre Messenger and Melemma. This is for the inference part, which is not active now. And there, it is the power from the power spectrum data. We have to extract the IGF and the source properties, basically at that density, at that time. And also it's compared with the your history, basically the ionization fraction or other parameters that are incorporated in the simulation, but that is later part. So we can focus on the first part now, and this will be 6 months in the duration, the foreground, and end of 2022 to up to 6 months, and the next is for the another 6 months is the inference pattern. And this is the web page for the data challenge 3. All the informations are there. What are the challenges and what are the computer resources they are providing us, and also how to register. So registration is already closed, but yeah, that is the registration process, and also some in that this is the total this is the web page they are showing, and this is the computational facilities that are providing for the different teams. So there are different computational facilities all over the world they are using. These are the supercomputer they will provide us. And this is the data science working group that can participate in that data challenge. Cosmic Dawn Epoch of Realization Cosmology Science Working Group, and also Continuum Science Working Group. These different groups, they are targeted so that people can join, and the data will be the visibility data and also the image. So both the Fourier space measurement and also the real space measurement, both will be there, because different algorithm work in different plane. The visibility is in the Fourier plane and the image is in the real sky plane. So they will provide the data in both frame. Now the challenge will be that I said we have to remove the foregrounds. You can use both, or you can use any of the data for the visibility or the image. And you have to remove properly the foregrounds, and we have to extract the cylindrical power spectrum and compare with the original 21 centimeter power spectrum that is already there in the data. And Catherine Trott and Vibha Jelic is the person who are main of that. And this is the data cube, what they have. In the simulated data, this is the cosmological signal. Then different types of foreground, extragalactic point sources, galactic synchrotron emission, and then gain error, and different types of gain error they have introduced in the data. And then they make a synthetic data cube by combining all of these. And this is the final data cube where everything is there. Now, using this image, they have simulated for the SK observation. So this is the diagram of the SK layout. This is the like a Christmas tree dipole antennas, and these 2256 this dipole combine one station, and there are 512 station in this format. And this is the total SK configuration they are considering, and this is the observation parameters. It was observed for the 4 hours, -2 hour angle to +2 hour angle, and they put some noise also, which is equivalent to 1000-hour noise, and they put the telescope at a certain point, that is the 0 and -30-degree pointing. And this is for SK low. This configuration is SK low. The SK mid is big side, but that is the different problem. And the data size is approximately 5.4 TB, but it can be reduced. Integration is 10 seconds. Channel width is 100 kilohertz, and this is the frequency range they covered, 106 to 196. And this is the image format they are providing. It is a 2048 cross 2048 cube. This is the image size, and this is the resolutions. And both the primary beam and the synthesized beam also they will provide, that we need for the normalization of the power spectrum. And now they will evaluate our result, if it is matching or not. This is the one, basically the figure of light, mainly you can say it's a chi-square. So you have the power spectrum at different k parallel and different mode, k parallel and k perpendicular. And you have measured something, and there are two they already know in the simulations, and you have to estimate the noise also, and you have to sum. So this is the quantity they are thinking to measure the accuracy of the measurement. So that is the challenge, and this is the different machine learning, all these things. But so this is the total data challenge that is there in that SK office. Now as a group, our work will be to test the different algorithms and remove the foregrounds, estimate the power spectrum, and compare. So for that, to testing our algorithm of the pipeline, they will provide one small data set, because the 5 TB data is quite large. It's very difficult to test our algorithm. So they promise to keep one development data set, which can be used for the testing purpose and all these things. And finally, they will put the actual data in their server, in that supercomputer facility they are providing. So the data will be there. After testing and validation, all the pipeline, copy all the things in their supercomputer and run this for the large data set. So that is the whole idea. we have to develop algorithm and we have to apply for the known data set. Yeah, when it is okay, just apply in the unknown data set for which they will large data set 5 dB. So that is the whole plan. Now I request all of the members uh, to come up with some of the ideas that we can apply for the foreground modeling or foreground subtraction. So yeah, so if you have any questions, so this is the whole data challenge. Yeah, if you have any questions, please.
When shall I get the data?
Huh?
When shall I get the data, the development data?
Oh, they development data, I think they will provide, but it is not now, but they will provide, I think. But I think they are now finalizing the teams that will be selected. But after that, I think they will give the development data. So that was that told, yeah.
So how do you suggest that we should try our techniques on what?
So that is the so just think about some algorithms, and within I think 1 month, actually our plan was to write the SK office that if they are on, but I think they will provide, but within 1 month I think they will get something.
Okay, maybe we can also simulate if it is possible.
That was also the plan, but SK's simulations is not that much simple that we are doing.
Okay.
It has not the deep shape antennas. It is a tracking more, sorry, deep scan antennas, and they use different delays to track a particular part of the sky. So this is a tracking mode in deep scan observation. So I think it will not be easy, but there are some pipelines. For example, the Oscar, they used mainly Oscar simulation package to simulate. So we can do that, but if they are already providing, so no need to spend time on the simulations. Just think about the actual data challenge is the foreground, all these things, because that will be another challenge for us also to simulate that.
Okay.
Any other questions? All for the 21 centimeter thing or the data challenge?
What is the computational resource that we are applying for? Like CPU, GPU.
For the actual thing?
Yes.
Okay, so that actually we sent some requirement that is in the proposal that I shared. So we told that these are the requirement we need. This is this much RAM, this much CPU hours, and this much GPU we need. Now they will allot something for us. So they actually sent me on an email that how, just to clarification, how much we need and what is the total RAM. So I clarified them, but hopefully they will allot something for us. But not sure which one we will get, but what we have requested, we will get. Any other questions? Okay, so let me stop the screen sharing. Okay, so now the idea is that I will share all the slides and the videos also, just to recap all these things if people are, and come up with some ideas how we can contribute to the actual data challenge. And then we will discuss more how to implement these ideas and how to remove the foreground and all these things. So that is the actually main idea. So that's what the before starting the actual challenge, just the motivation for organizing this talk was to get some overview of this field and what is the challenge, so that people can the people can involve more directly and contribute something in the actual data challenge. And we have time, so probably we'll start our group meeting, all these things from January first week. I'll send all the details soon, but within that time, so it will be good for each of the members come up with some of the ideas how we can contribute to the global community, that to measure the power spectrum accuracy and all these things. So, and all the test data and actual data regarding the computation, we will get hear from them also. So that is the whole plan.
It will be better if we can make a